Now, in this lecture, we'll answer on two questions. In the first question, we find out the area of this green shape that is inside square ABCD. And in the second question, we will find out the area of this green shape that is inside quarter circle AOB. So let's start with the first question. In the drawing, we have square ABCD. We know that line 7 PQ equals to 2 units in its length, line 7 QC equals to 3 units in its length. This is angle PQC, it is right angle, and our mission is to find out the area of actually quadrilateral PDQC. Okay, so first of all, we define one side of this square ABCD as A. So actually AB equals to A units in its length according to our definition. AD also equals to A. DC equals to A, and BC also equals to A according to our definition. We know that all the angles inside any square are right angles. So this is a right angle, this is a right angle, this is a right angle, and this is also a right angle. In the next step, we define the length of this line segment QB as X, and therefore AQ equals to AB minus QB. Again, AB minus QB equals to AQ. So AQ in total equals to AB, that is A, minus QB, that is X. So in total AQ equals to A minus X units in its length. In the next step, we define the size of this angle QCB as alpha, and we will focus on the right angle QBC. On the right angle QBC, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees. That is the sum of the angles in any triangle. In the next step, we focus. We know that AB is one side of square ABCD, therefore it is absolutely a straight line. So if we focus on this side of the straight line AB at point Q, here the sum of the angles must be equal to 180 degrees according to rule 3 that states that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at this side of the straight line AB at point Q? We have this angle that is 90 degrees minus alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to alpha. According to rule 3 that states that the sum of the angles on one side of a straight line is equal to 180 degrees. In this way we get that the sum of the angles on this side of the straight line AB at point Q equals to alpha plus 90 degrees minus alpha is 90 degrees. 90 degrees plus 90 degrees is equals to 180 degrees. That is the sum of the angles on this side of the straight line AB at point Q, exactly like rule 3. So in the right triangle APQ, this right angle APQ, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this third missing angle must be equal to 90 degrees minus alpha. According to the sum rule that says that the sum of the angles in any triangle is equal to 180 degrees. In the next step, I'll copy the right triangle APQ on this and this right triangle QBC in the equation. We prove that those two right triangles are similar to each other according to angle similarity rule. AQ equals to A minus X units in its length. AP is the missing side, and QP equals to 2 units in its length according to what is given us the question. Okay, those are the two right triangles. This is right triangle APQ, and this is the right triangle QBC that are covered on the original drawing. So in the next step, we prove that those two right triangles are similar to each other. So all those two right triangles are similar to each other. First of all, those triangles are both equal to alpha, therefore they are equal to each other. So actually, this is angle AQP. In the right triangle, APQ, and it is equal to this angle. This is actually angle QCB. In the right triangle, QBC. And again, I should found out that angle APQ in the right triangle AQP equals to angle QCB in the right triangle BCQ. They are both equal to alpha, therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So actually, this is angle APQ in the right triangle AQP, and it is equal to this angle. This is actually angle BQC in the right triangle BCQ. With again angle APQ in the right triangle AQP equals to angle QCB in the right triangle BQC. They are both angle APQ in the right triangle AQP equals to angle BQC in the right triangle BCQ. They are both equal to 90 degrees minus alpha, therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees and therefore they are equal to each other. So this is angle QAP in the right triangle APQ, and it is equal to this angle, it is actually angle QBC in the right triangle BCQ. So repeat again, I should found out that angle QAP in the right triangle APQ equals to angle BCQ in the right triangle BQC, they are both equal to 90 degrees and therefore they are equal to each other. So I can prove that all the triangles inside this right triangle APQ are correspondingly equal to all the triangles inside this right triangle QBC. And therefore, those two right triangles are similar to each other according to angle similarity rule. So I write it down. Found out afraid that the right triangle APQ is similar to the right triangle QBC according to angle similarity rule. So again, actually found out that the right triangle APQ is similar, this is the sum of similar to the right triangle QBC according to angle similarity rule. And for the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side AP in the right triangle APQ over side QB in the right triangle QBC is equal to side AQ in the right triangle APQ over side BC in the right triangle BCQ, and it is also equal to side QP in the right triangle APQ over side QC in the right triangle QBC. QC equals to 4 units in its line, QB equals to X, and BC equals to A. So in total, we should find out that AP over QB equals to AQ over BC equals to QP over QC. AP is the missing side, so we leave it as it is. So it is AP over QB. QB is X, so we substitute QB by X, and it is equals to AQ. AQ is A minus X, therefore we substitute AQ by A minus X divided by BC. BC is A, therefore we substitute BC by A, and it is equals to QP. QP is 2 over QC, that is 3. So in total, according to equation 1, we found out that AP over X equals to A minus X over A equals to 2/3. So those two expressions, they are equal to each other, therefore we get equation 1 from those two expressions that are equal to each other. So according to equation 1, A minus X over A is equal to 2/3. Here we cross multiply this equation 1, and we get that according to this equation 1, 3 times A minus X is equal to 2A. So here we'll open the brackets on this side of this equation 1. And finally we get that According to equation 1, 3 times a minus 3 times x equals to 2a. Here we subtract 2a from this equation 1, and finally get that 3a minus 2a is a, so a minus 3x equals to 0. So here we add 3x to this equation 1, and finally get that according to equation 1, a equals to 3x. Again, a equals to 3x according to equation 1. Those two expressions are equal to each other, therefore we create equation 2 from those two expressions that are equal to each other. So according to equation 2, we get that ap over x equals to 2/3. So write it down. According to equation 2, ap over x equals to 2/3. Here we multiply this equation by x, and finally we get that according to equation 2, ap equals to 2/3 times x. Again, according to equation 2, we should find out that ap equals to 2/3 x. In the next step, we'll copy the right triangle QBC in a new page, and we'll implement the Pythagoras theorem on this right triangle QBC. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse is equal to the sum of the squares of the perpendiculars. Here by PT is the relation for Pythagoras theorem. So actually, this is the right triangle QBC that are going from the original drawing. According to the Pythagoras theorem, this right triangle QBC, QC squared, that is the square of the hypotenuse, is equal to QB squared plus BC squared. So I write it down, this will be equation 3. So QC squared, that is the square of the hypotenuse, is equal to QB squared plus BC squared. QC is 3, therefore QC squared is 3 squared, that is 9, and it is equal to QB squared. QB is x, therefore QB squared is x squared plus BC squared. BC is 8, therefore BC squared is a squared. So in total, according to equation 3, we should find out that x squared plus a squared equals to 9. This is according to equation 3, but according to equation 2, we have already found out that a equals to 3, according to equation 1, we already found out that a equals to 3x. So I think now a equals to 3x according to equation 1. So in the next step, we substitute a squared in this equation 3 by 3x squared for this equation 1. And we get that according to equation 3, 9 equals to x squared plus a squared. A is 3x, therefore a squared is 3x squared. So in total we found out that according to equation 3, 9 equals to x squared plus 3x squared. So according to equation 3, 9 equals to x squared plus 3x squared. 3x squared is 9x squared. So in total I actually found out that according to equation 3, 9 equals to x squared plus 9x squared. So according to equation 3, 9 equals to x squared plus 9x squared is 10x squared. So I should found out that 9 equals to 10x squared according to equation 3. Here we divide this equation 3 by 10. And finally get that according to equation 3, 9 equals to x squared. Again, we divide the equation by 10 and get that according to equation 3, x squared equals to 9 over 10. Again, after we divided this equation by 3, we found out actually that x squared equals to 9 tenths. So here you take out of this equation 3, and finally get that according to this equation 3, x equals to the square root of 9, that is 3, over square root of 10. So in total we found out that according to equation 3, x equals to 3 over square root of 9 units. This is according to equation 3, but according to equation 1, we have already found out that a equals to 3x. So a equals to 3 times x, and x is 3 over square root of 10. So a equals to 3x, that is, and x is 3 over square root of 10. So in total, a according to equation 1 equals to 3 times 3, that is 9 over square root of 10 units in its length. Again, we found out that a, that is one side of square ABCD, is equals to 9 over square root of 10 units in its length. So write it down. We found out that this is side A, is equals to 9 over square root of 10 units in its length. What is the left of the missing line 7? Line 7 PD. From the drawing it is very easy to see that PD equals to AD minus AP. Again, AD minus AP equals to PD. So write it down. PD equals to AD minus AP. So PD in total equals to AD, that is A, and A is 9 over square root of 10 minus AP. So AD equals to 9 over square root of 10 minus AP. But according to equation 2, we have already found out that AP equals to 2/3 x. Again, AP equals to 2/3 x. Write it down. According to equation 2, AP equals to 2/3 times x. So according to equation 2, actually AP equals to 2/3 times x. And x according to equation 1 is equal to 3 over square root of 10. X is 3 over square root of 10. So in total we found out that AP equals to 2/3 times 3 over square root of 10. We have 3 in the numerator and 3 in the denominator, so 3 will get cancelled. So we cancel 3. Actually found out that AP equals to 2 over square root of 10. Repeat again, according to equation 2, actually found out that AP equals to 2 over square root of 10 units in its length. So PD equals to 9 over square root of 10 minus AP. And AP is 2 over square root of 10. So in total, PD equals to 9 over square root of 10 minus 2 over square root of 10 is 7 over square root of 10 units in its length. In total, we found out that PD, this is the missing 97 PD, that equals to 7 over square root of 10 units in its length. In the next step, we join points P and C together by a straight line. By joining points P and C, we can do two right triangles, the right triangle PDC and the right triangle QPC. Our mission is to find out the area of this green shape. So what is the area of the green shape? From the drawing, it is very easy to see that the area of the green shape in total equals to the area of the right triangle PDC, this right triangle PDC, plus the area of this right triangle PQC. And again, we found out the area of the green shape in total, it is equals to the area of the right triangle PDC plus the area of the right triangle PQC. So what is the area of this right triangle PDC? It is equals to the base of the triangle, that is PD, times the height to the base, that is DC, divided by 2. And again, the area of the right triangle PDC equals to the base of the right triangle PDC, that is PD, times the height to the base, that is DC, over 2, plus the area of the right triangle PQC. What is the area of this right triangle PQC? From the drawing, it is very easy to see that the area of the right triangle PQC equals to the base of the right triangle PQC, that is PQ, times the height of the base, that is QC, divided by 2. And again, the area of this right triangle PQC equals to the base of the right triangle, that is PQ, times the height of the base, that is QC, over 2. So in total, the area of this green shape is equal to PD. PD is 7 over square root of 10 plus times DC. DC is 9 over square root of 10 divided by 2. So again, as I found out that PD is 7 square root of 10 times DC, that is 9 over square root of 10 divided by 2, plus the area of the right triangle PDC, PQC. The area of the right triangle PQC is equals to PQ, that is 2, times QC, that is 3, divided by 2. So again, the area of the right triangle PQC equals to 2 times 3 over 2. So in total, the area of the green shape is equals to, here we have 7 times 9 is 63, over square root of 10 times square root of 10 is 10. So in total, this expression equals to 63 over 10 over 2. Plus, here we have 2 over 2 is 1, so this expression in total equals to 3. So the area of the right triangle, the green shape, it is equals to 63 over 10 over 2 is 63 over 2 times 10, that is 20, plus 3. So here we multiply 3 by 20 and then we divide it by 20 in order to become proper with this number. And we get that in total the green shape equals to 63 plus 3 times 20 is 60 divided by 20. So in total the green shape is equal to 60 plus 63 is 123 divided by 20. And in terms of numbers, 123 divided by 20 is 6.15 square units. Because again, if we found out that they have this green shape, it is equals to either 123 over 20 square units, so in terms of numbers, they have this green shape is equal to 6.15 square units. Okay, so we finish with the first question. In the next step, I will present to you the second question and we will solve it. Our mission in this second question is to find out the area of this green shape. So in the drawing we have quarter circle AOB. We know that the radius of this quarter circle AOB is 5 because OB equals to 5. In addition, this is a right angle AOB equals to 90 degrees in its size because AOB is a quarter circle. This is also a right angle, that is to say angle QNO is a right angle. This is also a right angle, so angle PMO is also a right angle. In addition, we know that arc AP equals to arc PQ equals to arc QB. Again, our mission is to find out the area of this green shape. So first of all, we'll join points O and P together by a straight line, and we'll also join points O and Q together by a straight line. So here we can implement rule 20. Why? Because we know that arc AP equals to arc PQ equals to arc QB. So repeat quickly rule 20. According to rule 20, in front of equal arcs there are equal central angles. So in the domain we have a circle, and we know that this is arc AB, that equals in its length to this arc CD. And according to this rule, in front of equal arcs, there are equal angles. There are equal central angles. So in front of this arc AB, we have this central angle, angle alpha. In front of this arc CD, we have this central angle, angle beta. And according to this rule 20, because of the fact that those two central angles they are both located in front of those two equal arcs, they must be also equal to each other. That is to say, angle alpha equals to angle beta. So we can implement rule 20 in our drawing. Why? Because in our drawing, it is given us the question that arc AP equals to arc PQ equals to arc QB. So in front of this arc AP, we have this angle, angle AOP, central angle AOP. So we define the size of central angle AOP, this angle is angle X. And in front of this arc PQ, we have angle POQ. and because of the fact that those two arcs are equal to each other in their lengths, therefore the angles that are located in front of them must be also equal to each other. So this set triangle POQ must be also equal to x units in its size. Likewise, we have arc QB equals to arc QP equals to arc AP. Therefore, in front of this arc QB, we have this center angle QOB, and therefore the size of this center angle QOB must be also equal to x degrees in its size. Okay, so in total we found out that center angle AOP equals to center angle POQ equals to center angle QOB. They are both equal to x degrees in their sizes. But we also know that AOB is a quarter circle, and because of the fact that AOB is a quarter circle, it means that this angle AOB equals to 90 degrees in its size. So in total, the sum of those two center angles, x, and x, in total the sum of those two angles must be equal to 90 degrees. Because angle AOB equals to 90 degrees. So I write it down. Actually we found out that the sum of those two center angles is 3x, and 3x must be equal to angle AOB, that is the right angle. This is equal to 90 degrees in its size. Here we divide, so 3x equals to 90 degrees. Here we divide this equation by 3, and finally we get that the missing angle A is equals to 90 degrees over 3 is 30 degrees. So each angle, the center angle, is equal to 30 degrees in its size. Center angle AOP equals to 30 degrees in size, center angle POQ also equals to 30 degrees in size, and this is center angle QOB, this is also equals to 30 degrees in its size. Okay, so we'll focus on the right triangle MOP. The right triangle MOP, this angle equals to 30 degrees, this angle equals to 90 degrees, therefore this third missing angle must be equal to 60 degrees in its size. According to the rule that the sum of the angles in any triangle is equal to 180 degrees. So 60 degrees plus 30 degrees is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees, that is the sum of the angles in any triangle. Likewise, we'll focus on the right triangle NQO. In this right triangle NQO, this angle equals to 90 degrees, this angle in total equals to 30 degrees plus 30 degrees, that is 60 degrees, and therefore this third missing angle must be equal to 30 degrees in its size. According to the sum rule that states that the sum of the angles in any triangle is equal to 180 degrees. So in the next step, I'll copy the right triangle MPO on this, and this right triangle NQO in a new page, and we'll prove that those two right angles can go into each other according to angle side angle rule. So actually, this is the right triangle NPO that I copied from the original domain. So I copy this right triangle NOQ in this new page, and then we prove that those two right angles can go into each other according to angle similarity rule. So actually, this is the right angle NQO that are going to the original domain. So in the next step we prove that those two right angles can go into each other according to angle side angle rule. So why those two right angles can go into each other? First of all, those two angles are both equal to 60 degrees and therefore they are equal to each other. So actually, this is angle MPO in the right triangle MPO, and it is equal to this angle. This is actually angle NOQ in the right triangle NQO. So if it again, angle MPO in the right triangle, angle MPO in the right triangle MOP equals to angle NOQ in the right triangle NQO. They are both equal to 60 degrees and therefore they are equal to each other. In addition, this is side OP is equal to side OQ. They are both the area of this quarter circle that is equal to 5 and therefore they are equal to each other. So OP equals to OQ equals to 5. OP in the right triangle NPO equals to OQ in the right triangle NQO. They are both the area of the circle is equal to 5 and therefore they are equal to each other. And finally, those two angles are both equal to 30 degrees and therefore they are equal to each other. So actually, this is angle MOP in the right triangle MPO, and it is equal to this angle. This is actually angle NQO in the right triangle NOQ. So repeat again, angle MOP in the right triangle MPO equals to angle NQO in the right triangle NOQ. They are both equal to 30 degrees and therefore they are equal to each other. So actually proved that those two angles and the side that included between those two angles, that is side OP, are correspondingly equal to those two angles and the side that included between those two angles, that is side OQ and the right triangle NQO. Therefore those two right triangles can go into each other according to angle side angle rule. So I write it down. I actually found out that the right triangle MPO congruent, this is the sign of congruent, to the right triangle NQO. According to angle side angle rule. Okay. We have those two angles and the side that is, OP that is between those two angles in the right triangle MPO corresponding equal to those two angles, and the side OQ that is included between those two angles in the right triangle NQO. And therefore those two right triangles can go into each other according to angle side angle rule. And from the fact that triangle MPO can go into triangle NQO, we will derive that they have also the same areas. That is to say, the area of the right triangle MPO is equal to the area of the right triangle NQO. Okay, so this is equation 1. The area of the right triangle MPO consists of, here we define intersection point between PO and AQ, and this point is point S. So the right triangle MPO consists of quadrilateral MPSN and this small right triangle NSO. So in total, the area of the right triangle MPO must be equal to the area of quadrilateral MNSP, this paint quadrilateral, plus the white right triangle NSO. So I write it down. The area of the right triangle MPO is equal to the area of this green quadrilateral MPNS plus the area of this white right triangle NSO. Repeat again. Because of the fact that the right triangle MPO consists of quadrilateral MP and S and the small white right triangle NSO, which means that the area of the right triangle MPO must be equal to the area of quadrilateral MP and S plus the area of the right triangle NSO. And if we found out that the area of the right triangle MPO equals to the area of the right triangle NQO. So what is the area of the right triangle NQO? This is the right triangle NQO. This right triangle NQO consists of two triangles. Triangle NSO, this triangle SQO. And because of the fact that triangle NQO consists exactly two triangles, it means that the area of this right triangle NQO must be equal to the area of triangle NSO plus the area of this triangle, triangle SQO. So let it down. So the area of this right triangle NQO must be equal to the sum of the two areas that the right triangle consists of. The right triangle NQO consists of the right triangle NSO, so it is the area of the right triangle NSO plus the area of this triangle SQO. So repeat again, because of the fact that triangle NQO consists of two smaller triangles, therefore the area of the big triangle NQO must be equal to the sum of the areas of the two triangles that triangle NQO consists of. Okay, so in total the area of the right triangle NQO must be equal to the area of the small triangle NSO plus the area of the small triangle SQO. So this is equation 1. In this equation 1, we have on both sides of the equation the area of the right triangle NSO. So we will cancel this right triangle NSO because it appears on both sides of the equation 1. So thereof the right triangle NSO will get cancelled. After I cancel thereof the right triangle NSO, we're left only with quadrilateral M, P, and S. According to this equation 1, the area of quadrilateral M, P, and S is equal to the area of the right triangle SQO. So I write it down. In total, we should found out that the area of the right of quadrilateral, according to equation 1, the area of quadrilateral M, P, and S is equal to the area of triangle SQO. Okay. So here the area of this quadrilateral MP and S is equal to the area of this triangle SQO. So if we define the area of this triangle MPSNSA, according to equation 1, it is equal to the area of triangle SOQ. Therefore, the area of triangle SOQ, this triangle, must be also equal to A, because they are equal to each other. Our mission is to find out the area of this green shape. So what is the area of the green shape? So from the drawing it is very easy to see that the area of the green shape in total equals to the area of quadrilateral MP and S. That equals to A according to our definition. Quadrilateral MP and S plus the area of this shape PSQ. Plus shape PQS. Repeat again. From the drawing it is very easy to see that in total the area of this green shape equals to the area of this quadrilateral MNSP plus the area of this shape PQS. So repeat again. The area of the green shape in total equals to the area of quadrilateral MP and S plus the area of the shape PQS. But we have already found out that the area of this quadrilateral MNSP equals to the area of this triangle OQS. So we can substitute the area of this green quadrilateral MP and S by the area of this triangle SQO. So we'll do it now, and we get that the area of the green shape in total equals to the area of shape PQS plus the area of quadrilateral MP and S, but the area of quadrilateral MP and S equals to the area of triangle QSO. So we substitute the area of quadrilateral MP and S by the area of this triangle QSO. So total we found out that the area of this green shape is equals to the area of triangle QSO plus the area of this shape PSQ. And the sum of those two areas is equal to the area of this sector POQ. Again, the sum of those two areas, it is equal to exactly to the area of this sector POQ. Again, the sum of the two areas, shape PQS plus the area of triangle QSO, in total it is equal to the area of sector PQO. So in total we should found out the area of this green shape is equal to the area of sector PQO. So what is the area of sector PQO? The area of sector PQO equals to pi r squared, that is the area of the circle, times the angle between the legs of sector POQ, that is 30 degrees, over 360 degrees. Repeat again, the area of sector PQO in total is equals to pi r squared, that is the area of the circle, times the angle between the legs of the sector, that is 30 degrees, over 360 degrees. We know that the radius r of this quarter circle equals to 5. So pi r squared is pi times 5 squared, that is 25 pi, times 30 over 360 degrees is 1 over 12. So in total we found out that the area of the green shape equals to either 25 pi over 12 square units, or in terms of numbers, the area of the green shape is equal to 6.545 square units. I check again that I'm not wrong. The area equals to 25 pi over 12. It is 6.545 square units. But again, I should found out that the area of this green shape equals to either 25 pi over 12 square units, or in terms of numbers, the area of this green shape is equals to 6.545 square units. So finish with the second question. In the next step, I'll summarize the lecture. We'll start with the first question, of course. In the first question, our mission was to find out the area of this green shape. So in the drawing, we have ABCD is a square, and we know that this is side QC that is equals to 4 units in its length, this is side PQ that is equals to 2 units in its length. In addition, we know that this is angle PQC, that is the right angle. Again, our mission is to find out the area of this green shape, that is actually the area of quadrangle QPDC. Okay. So first of all, because of the fact that ABCD is a square, we know that all the sides in any square are equal to each other. So we define one side of square ABCD is say, so AD equals to DC equals to BC equals to B8. Each side is equal to A according to our definition. We also know that all the angles inside any square are right angles. So those 4 angles are all right angles. In the next step, we define the length of this line segment QB as X. We know that AB equals to A according to our definition. Therefore, AQ must be equal to AB, that is A, minus QB, that is X. So in total, AQ equals to A minus X. AQ equals to A minus X units in its length. Because it is AB, that is A, minus QB, that is X. So in total, AQ equals to A minus X. In the next step, we define this angle QCB as alpha. So in the right angle QBC, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees. And 90 degrees plus 90 degrees is equal to 180 degrees. That is the sum of the angles in any triangle. we know that AB is one side of square ABCD. So AB is the side of a square ABCD. It is absolutely a straight line. So if we focus on this side of the straight line AB at point Q, here the sum of the angles must be equal to 180 degrees according to rule 3 that says that the sum of the angles from one side of a straight line is equal to 180 degrees. So which angles we have at this side of AB at point Q? We have this angle that is 90 degrees minus alpha, plus this angle that is 90 degrees according to what is given in the equation, plus this missing angle. Total the sum of those three angles must be equal to 180 degrees according to rule 3. Therefore this missing angle must be equal to alpha degrees in its side. Why? Because alpha plus 90 degrees minus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles on one side of a straight line according to rule 3. So this angle must be equal to alpha. So in the right angle APQ, this angle equals to alpha, this angle equals to 90 degrees. Therefore this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. So in the next step, I copied this right angle APQ and this right angle QBC in a new page, and we proved that those two right angles are similar to each other according to angle similarity rule. So actually, this is right angle APQ and this is right angle QCV that are coming from the original drawing. So why those two right angles are similar to each other? First of all, those two angles are both equal to alpha, therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So actually found out that all the angles inside the right angle APQ corresponding equal to all the angles inside this right angle QBC. And therefore those two right angles are similar to each other according to angle similarity rule. And from the fact that those two right angles are similar to each other, we derive that the following relationship exists between their sides. We derive that AP over QB equals to AQ over BC equals to QP over OC. AP is the missing side, so limited it is QB is X, AQ is A minus X, BC is A, QP is 2, and QC is 3. So in total, according to equation 1, we shall find out that AP over X equals to A minus X over A, and it is equals also to 2/3. So here, those two expressions are equal to each other, so we can get the equation 1 from those two expressions that are equal to each other. So if we found out that according to equation 1, A minus X over A equals to 2/3. Okay, so here of course multiply this equation and finally found out that 3 times A minus X equals to 2A. Here we open the bracket, so this side of this equation 1, and finally found out that 3A minus 3X equals to 2A. Here we subtracted 2A from this equation 1, and finally found out that 3A minus 2A is A, so A minus 3X equals to 0. We added 3X to this equation, and finally found out that A equals to 3X according to this equation 1. Here in this equation, this long equation, actually this long equation is the same. Those two expressions are equal to each other, so we can add equation 2 from those two expressions that are equal to each other. So we found out that AP over X equals to 2/3. AP over X equals to 2/3. Here we multiply this equation by X and finally found out that according to this equation 2, AP equals to 2/3 times X. In the next step, I copied this right angle QBC in a new page and implemented the Pythagoras theorem on this right angle QBC. Actually, this is the right triangle QBC that is coming from the original drawing. According to the Pythagoras theorem, in this right triangle QBC, QC squared, that is the square of the hypotenuse, is equal to QB squared plus BC squared. QC is 3, therefore QC squared is 3 squared, that is 9, and it is equal to QB squared. QB is x, therefore QB squared is x squared plus BC squared. BC is 8, therefore BC squared is a squared. So in total, actually, according to equation 3, we found out that 9 equals to x squared plus a squared. This is according to equation 3, but according to equation 1, we have already found out that a equals to 3x. If a equals to 3x, this means that a squared must be equal to 3x squared. Therefore, we can substitute a squared in this equation 3 by 3 squared from equation 1. We did it, and we can find out that according to this equation 3, 9 equals to x squared plus a squared is 3x squared, according to equation 1. So in total, we found out that according to equation 3, 9 equals to x squared plus 3x squared. So 9 equals to x squared and 3x squared is 9x squared. So in total, according to equation 3, we found out that 9 equals to x squared plus 9x squared. X squared plus 9x squared is 10x squared. So in total, according to equation 3, we found out that 9 equals to 10x squared. Here we divided this equation 3 by 10, and finally found out that according to this equation 3, x squared equals to 9 over 10. Here we took a root out of this equation 3, and finally found out that x equals to the square root of 9, that is 3, over square root of 10. So in total, according to equation 3, we should found out that x equals to 3 over square root of 10. This is according to equation 3, but we already found out that according to equation 1, a equals to 3x. So a equals to 3x, and x, according to the equation 3, is 3 times square root of 10. So a equals to 3x, and x is 3 times square root of 10. So in total, according to equation 1, a equals to 3 times 3, that is 9 over square root of 10. Again, according to equation 1, we found out that a equals to 9 over square root of 10. DC equals to a, and a equals to 9 over square root of 10 units in its length. According to equation 1, we already found out that AP equals to 2/3 times x. So AP equals to 2/3 times x, and x is 3 over square root of 10. So in total, AP equals to, here we have 3 in the numerator and 3 in the denominator, so 3 will get cancelled. And we should have found out in total, after we cancelled 3, we found out that AP equals to 2 over square root of 10 units in its length. So this is side AP is equals to 2 over square root of 10 units in its length. So we know that AB equals to 2 over square root of 10 units in its length. Our mission is to find out the area of this green shape. But if AP equals to 2 over square root of 10, PD must be equal to AD minus AP. Again, PD equals to AD minus AP. Okay, so PD equals to AD minus AP. So PD in total equals to AD, that is 9, AD that is 8, that is equals to 9 over square root of 10, minus AP that is 2 over square root of 10. So in total, this line segment PD equals to 9 over square root of 10 minus 2 over square root of 10. 9 over square root of 10 minus 2 over square root of 10 is 7 over square root of 10 units in itself. In total, we should find out that, let me say, line segment PD is equals to 7 over square root of 10 units in its length, and A equals to 9 over square root of 10 units in its length. Our mission is to find out the area of this green shape. The next step, actually, join points P and C together by straight line. By joining points P and C, we get the right triangle PQC and this right triangle PDC. It is obvious that the area of this green shape equals to the sum of the areas of those two right triangles. That is to say, the area of the green shape in total must be equal to the area of the right triangle PDC plus the area of the right triangle PQC. Again, the area of the green shape in total equals to the area of this right triangle PDC plus the area of this right triangle PQC. So the area of the green shape in total is equal to the area of the right triangle PDC equals to the base of the triangle times the height over 2. The base is PD, the height is DC over 2. So in total, the area of the right triangle PDC equals to the base that is PD times the height of the base that is DC over 2. Plus the area of this right triangle PQC. The area of the right triangle PQC equals to the base of the triangle that is PQ times the height to the base that is QC over 2. Okay, again, the area of this right triangle PQC in total is equal to the base that is PQ times the height of the base that is QC over 2. PD is 7 over square root of 10 times DC that is 2 or that is 9 over square root of 10 divided by 2 plus PQ is 2 times QC that is 3 divided by 2. Here we have 7 times 9 is 63, square root of 10 times square root of 10 is 10. So in total this expression is equal to 63 over 10 divided by 2. Plus here we have 2 over 2 is 1, so in total this expression equals to 3. So in total we should find out the area of the green shape equals to 63 over 10 over 2 plus 3. 63 over 10 over 2 equals to 63 times 10. 63 times 10, 63 over 10 times 2 is equals to 63 over 10 times 2. 10 times 2 is 20. So in total the area of the green shape equals to 63 over 20 times 3. Here we multiplied 3 by 20 and then we divided by 20. We divided it by 20 in order to have a common factor of this expression. And finally found out that the area of the green shape in total equals to 63, and 3 times 20 is 60 divided by 20. So in total the area of the green shape equals to 63 plus 60, that is 123 over 20. So we found out that the area of this green shape equals to either 123 over 20 square units, so in terms of numbers, the area of this green shape is equal to 6.15 square units. Okay, so finish with the first question. In the next step, I presented to you the second question and we solved it. In the second question, our mission is to find out the area of this green shape. So, in the drawing, we have quarter circle A or B. We know that this is angle PMO, that is a right angle. This is angle QNO, that is also a right angle. In addition, we know that the radius of this quarter circle OB equals to 5. We know also that arc AP equals to arc PQ equals to arc QB. Again, our mission is to find out the area of this green shape. So in the first step, we join points O and P together by side line, and join points O and Q together by straight line. So here, because of the fact that that arc AP equals to arc PQ equals to arc QB, we can implement rule 20. So PQ rule 20, according to rule 20, in front of equal arcs, there are equal central angles. So in the drawing we have a circle, and we know that this is arc AB, that is equal to this arc CD. So according to this rule 20, in front of those two equal arcs, there are equal central angles. So this is the central angle alpha, that must be equal to this central angle beta, because of the fact that those two central angles are located in front of those two equal arcs, and therefore they are equal to each other. That is to say, alpha equals to beta. So we can actually implement rule 20 in our drawing. Because in our drawing we have arc AP equals to arc PQ equals to arc QB. And according to rule 20, in front of equal arcs, there are equal central angles. So those two angles, 1, 2, 3, they are all located in front of those two equal arcs, AP, PQ, and QB, and therefore they are equal to each other. So if this angle is x, then this angle must be also equal to x, and this center angle must be also equal to x degrees in its side, right? Because of the fact that all those center angles they are located in front of equal arcs, and therefore they must be also equal to each other. So if one angle is x, then the other angles must be also equal to x degrees in their sizes. So this is x, and this is x. So in total, the sum of those two angles is x plus x plus x, that is 3x. So angle AOB equals to 3x from one side, but angle AOB is also a right angle from the other side because it is a quarter circle. In any quarter circle, this angle is a 90 degrees. So in total, we found out that 3x, that is the sum of those three angles, is equal to 90 degrees. 3x equals to 90 degrees. We divided this equation by 3 and found out that the missing angle x equals to 90 degrees over 3 is 30 degrees. So this angle is 30 degrees, this angle is 30 degrees, and this angle is also 30 degrees. Okay, so in the next step, we know that in the right triangle NOQ, this angle equals to 30 degrees plus 30 degrees is 60 degrees. This angle equals to 90 degrees, and therefore this third missing angle must be equal to 30 degrees in its size. According to the rule, that the sum of the angles in the triangle is equal to 180 degrees. So 60 degrees plus 30 degrees is 90 degrees, and 90 degrees plus 90 degrees, it is 180 degrees. It is the sum of the angles in any triangle. Likewise, in the right triangle NPO, this angle equals to 30 degrees according to rule 20. This angle equals to 90 degrees according to what is given as the equation, and therefore this third missing angle must be equal to 60 degrees in its size according to the sum rule that says that the sum of the angles in any triangle is equal to 180 degrees. So in the next step, I copied the right triangle MPO on this side, and this right triangle NQO in a new page, and we proved that those two right triangles can go into each other according to side angle rule. Okay, this is the right triangle MPO that I copied from the original drawing, and this is the right triangle NQO that also copied from the original drawing. So why those two right triangles can go into each other? First of all, those two angles are both equal to 30 degrees, and therefore they are equal to each other. In addition, those two angles are both equal to 60 degrees, and therefore they are equal to each other. And finally, PO equals to QO. They are both the area of the quarter circle, and therefore they are equal to each other. Repeat again. PO equals to QO. They are both the area of the circle, is equals to 5, and therefore they are equal to each other. So in total, we found out that those two angles and the side that is included between those two angles, that is side PO, are corresponding equal to those two angles, and the side that is included between those two angles, that is side QO in the right triangle and QO. And therefore those two right triangles can go into each other according to angle side angle rule. We have two angles, and one side in this triangle are corresponding equal to two angles, and one side of the other triangle. Therefore those two right triangles can go into each other according to angle side angle rule. And from the fact that those two right triangles can go into each other, we will derive that they have also the same areas. Okay? Because of the fact that those two triangles can go into each other, they have also the same areas. That is to say, the area of the right triangle MPO must be equal to the area of the right triangle MQO. But what is the area of the right triangle MPO? The area of the right triangle MPO, this is the right triangle MPO. It consists of quadrilateral MNPS, and it also consists the right triangle NSO. So the sum of the quadrilateral plus the sum of this right triangle NSO is equal in total to the area of triangle MPO. So here, the area of the right triangle MPO equals in total to the area of quadrilateral MP and S plus the area of the right triangle NSO, and it is equal to the area of triangle NQO. This is the right triangle NQO. It is very easy to see from the drawing that this right triangle NQO consists of two small triangles. The small right triangle NSO and this right triangle SQO. Therefore, the sum of the area of the small right triangle NSO plus the area of this right triangle SQO in total it is equal to the area of the big triangle NQO. Repeat again. The area of the right triangle NQO is equal to the area of the small right triangle NSO plus the area of triangle SQO, because it consists of those two small triangles. So here we have the area of the right triangle NSO on both sides of equation 1, so we cancel the area of the right triangle NSO, and we left only with those two expressions. So what we found out in total, the area of quadrilateral MPNS is equal to the area of the triangle SQO. So this is the area of triangle of quadrilateral MPSN, and it is equal to the area of this triangle SQO according to equation 1. So if we define the area of this green quadrilateral MPSN SA, then the area of this triangle SQO must be also equal to A, because they are equal to each other with their areas. So if the area of quadrilateral MPSN is 8, therefore then the area of this triangle OSQ must be also equal to A. Okay, so in total we found out the area of quadrilateral MPNS equals to the area of triangle SQO. Our mission is to find out the area of this green shape. For the dome, it is very easy to see that the area of this green shape equals to the area of quadrilateral MPSN plus the area of this green triangle PQS. Repeat again. The area of the green shape equals to the area of quadrilateral MPNS plus the area of triangle PQS. Okay, so the area of the green shape equals to the area of triangle PQS plus the area of quadrilateral MPSN. But we already found out that the area of quadrilateral MPSN equals to the area of triangle QSO. So we can substitute the area of this quadrilateral MPSN by the area of this triangle QSO. So here we substitute the area of this quadrilateral MPNS by the area of triangle QSO. And finally found out that in total the area of the green shape equals to the area of shape PQS plus the area of triangle SQO. So in total the sum of those two areas is equal to the area of sector POQ. It's very easy to see the area of this green shape PSQ plus the area of this triangle QOS. In total it is equal to the area of sector POQ. Okay. In total the area of the shape PQS plus the area of triangle QSO, it is equal to the area of sector PQO. So what is the area of this sector PQO? Actually the area of sector PQO must be equal to the area of the circle, that is pi r square, times the angle between the legs of this sector, that is 30 degrees over 360 degrees. I repeat again. The area of sector PQO in total equals to the area of the circle, that is pi r square, times the angle between the legs of the circle, that is 30 degrees over 360 degrees. So in total the area of this sector PQO, that is the area of this green shape, is equals to pi r square. R is 5, therefore r square is 5 squared, that is 25. So in total pi r square is pi 5 squared, that is 25 pi. And 30 degrees over 360 degrees is 1 over 12. So in total we found out that the area of this green shape equals to either 25 pi over 12 square units, so in terms of numbers, the area of this green shape equals to 6.545 square units. And repeat again, the area of this green shape equals to either 25 pi over 12 square units, so in terms of numbers, the area of this green shape equals to 6.545 square units. Okay, thank you very much.